Hello, my name is Irfan Azim. In this presentation, I'm going to describe a new ionospheric total electron content measurement capability from ocean buoys, and I will also show first results from a pair of buoys in the middle of the Pacific Ocean. I would also like to acknowledge my co-authors, Jeff Crowley and Victoria Forsyth, both from Astra. Before I dive into the presentation, I would like to acknowledge support from the Air Force Small Business Innovation Research Program that funded this study. I'm also very appreciative of NOAA National Data Buoy Center for hosting Astra's GPS receivers on their buoys. Without their support, we wouldn't have been able to make the TEC measurements that are the focus of this presentation. So the motivation for this work came from the fact that currently there are no existing arrays of GPS receivers in the Oceanic region for receiving and processing TEC data. We have all become fairly accustomed to using TEC data from ground-based GPS receivers. Over the last decade, TEC measurements from dense networks of GNSS receivers worldwide have provided an important database to study the ionosphere. GNSS receivers have enabled researchers to create TEC maps to study ionospheric responses to geomagnetic and lower atmospheric disturbances. However, to date, these networks of GNSS receivers have only been deployed on land. And this situation is illustrated in the figure on the right. The figure shows GNSS TEC measurements from globally distributed GNSS receivers, and one can see most of the data is actually over the land masses. And wherever we have in oceans, we don't have TEC data. So this leaves 7/10 of the Earth without an adequate observational coverage for ionospheric studies. A new generation of GPS receivers operating in the maritime are needed to fill this critical gap in obtaining real-time ionospheric TEC and simulation data from the Oceanic region. And in this presentation, I'll describe a new capability for ionospheric remote sensing using GPS receivers that are designed specifically for operations from ocean buoys. And I would also want to say that this figure was actually generated using the data from the medical database. So in this study, I'll give a very high level overview of a small size, weight, and power GPS receiver that is designed for operations of ocean surface buoys. I will also then present first results of TEC measurements using these GPS receivers on a pair of oceanic buoys in the Pacific Ocean. And I'll also present some comparisons of the measured TEC data with our I-2016 model that were done as an initial exercise for data validation. So the GPS receiver that we have used for this study is called Rio. Rio stands for Remote Ionospheric Observatory. It is a dual frequency science grade GPS receiver that tracks the traditional L1 civil signal and the L2 civil signal, or L2C. Rio builds on the heritage of Astra's CASES GPS receiver. It provides the same functionality as the original CASES GPS receiver, but in a much smaller package and a reduced power consumption. In contrast to CASES, the Rio GPS receiver uses only 2.5 watts of power and is about 4.25 inches by 4.5 inches by 2.5 inches in length, width, and height. The Rio receiver design is optimized for operations in remote locations, including ocean deployments where power and other resources may be extremely limited. And the figure here shows the Rio receiver in its current commercial product form. The figure at the bottom just shows a block diagram of the key components of the Rio GPS receiver. I'm not going to go into too much detail, but the main takeaway here is that the Rio receiver design also includes a low power onboard computer that does all the processing of the raw GPS observables to provide TEC and scintillation data. In this presentation, I'm not going to talk about the scintillation products because they're being validated, but I'm going to mainly focus on the TEC data. So for this study, we built and deployed 2 Rio GPS receivers on the existing NOAA tropical atmosphere ocean buoys, or TAO buoys, in the Pacific Ocean. The Rio receivers were integrated with Astra's standalone system support module, or SSMs, to support autonomous operation and data exfiltration. The picture on the right shows a TAO buoy, which consists of a fiberglass foam float and a aluminum tower and a stainless steel brittle. The figure in the middle shows a CAD drawing showing the placements of the Rio GPS receiver's electronic enclosure. It's basically a box here supporting solar panels and the GPS antenna, whereas the figure on the left shows the locations of the 2 Rio GPS receivers in the middle of the Pacific Ocean. While each TAO buoy includes data logging, telemetry, and battery systems to support various meteorological sensors, we only use the platforms as a mean for mechanically mounting our receiver to the buoy. And this was done deliberately so as not to interfere with the NOAA's mission critical measurement. So the Rio system that were designed for TAO buoys included their own telemetry, thermal management, and power subsystems, allowing them to operate independently of other sensors and systems on the buoy. Each Rio is housed in a weatherproof and corrosion-resistant enclosure, along with a radium communication modem, an overvoltage protection system, low power alarms, and advanced power management controller to protect electronic equipment from catastrophic events. In August 2018, 2 Rio receivers called Rio 12 and Rio 15 were deployed on the NOAA TAO buoys. The picture here, or the figure here, shows the locations of Rio 12 and Rio 15. The white line is the geomagnetic equator. Rio 12 is located at 5 degrees geographic north. Rio 15 is located at 2 degrees geographic north. The TAO array consists of approximately 70 moored buoys in the tropical Pacific Ocean, and here's a picture of the TAO array. And Rio 12 and 15 were located along these 2 chains of TAO array. So in the next few slides, I'm going to present or discuss some of the summary plots of TEC measurements from Rio 12 and Rio 15 from September 1st, 2018 to the end of 2019. So first, I'm going to show TEC measurements from September 1st to December 31st, 2018. The top plot shows Rio 12 TEC measurements as a function of local time and the day of the year. The middle panel is Rio 15 TEC, whereas the bottom panel shows the DST and KP indices. DST is in red, KP is shown in blue. Both receivers show the dayside increase in TEC between 10 and 18 local time, which is driven by the plasma generation from solar illumination. On average, the peak daytime TEC values are about 30 TeQ during the equinox months and 22 TeQ during December. Comparing the TEC enhancements and DST, there's a clear association between TEC enhancement and DST excursions during storm times throughout the year. So and these storms, they're very big. They're fairly modest geomagnetic storms where DST got down to maybe just about -50 nanotesla. This slide shows TEC results from Rio 12 and Rio 15 for the entire year of 2019 from January 1st to the end of December 2019. Again, the top panel shows Rio 12 TEC as a function of local time and day of year. The middle panel is Rio 15 TEC, and the bottom panel shows the KP and DST indices for 2019. Again, they are the DST and KP data shows several moderate geomagnetic storms interspersed throughout the observation period in 2019. And again, we see a clear association between TEC enhancements and the DST excursions. The TEC seem to increase rapidly at the storm onset and remain elevated for at least several days during the recovery period. The behavior of TEC during storm times has been reported previously by several studies, including Minucci et al. 2005. And the main driver of this storm time increase in the dayside TEC is the eastward directed prompt penetration electric field of magnetospheric origin and the associated upward E cross B drifts at the equator, which lifts the plasma upwards and raises the layer to altitudes where recombination rates are low. Next, we compared the measured TEC with RI 2016. Left panel shows TEC data plotted in blue compared with RI TEC, which is shown as red crosses for 4 individual days, September 1st, December 1st of 2018, and then January 15th and July 23rd of 2019. So this was done to assess the overall quality of the TEC data from the Rio receivers. And again, we see in general there is a good agreement between the RI model and the measured TEC. And there's 2 panels on the right. We compare Rio 12, or this is and the panels on the right, this is the scatter plot between hourly averaged TEC data from Rio 12 and Rio 15 plotted against IRI predicted TEC measurements. And again, we'll see a very good agreement between the model and data. The correlation coefficient is 0.902 for Rio 12, whereas the correlation coefficient is 0.890 for Rio 15. And in this slide, we show the seasonal climatology of the measured TEC from Rio 12. Here we show seasonally averaged local time variation of 5-minute average TEC data from Rio 12. And here we have these seasonal averages were formed using all available data between September of 2018 and between September of 2018 and December of 2019. The gray shaded region represents 1 sigma standard deviation. Comparing the peak TEC values across different panels in this figure, we observe that there are annual and semi-annual variations, with maxima near the equinox, a primary minimum near the June solstice, and a secondary minimum near the December solstice. Similar annual and semi-annual variations have been reported in the daytime NMF2 and HMF2 data from Cosmic Mission by Burns et al. And similar seasonal averages were also computed for Rio 15, which show identical features. So as a result, we don't show them here. So in summary, in this presentation, we have described a new low-power dual-frequency GPS receiver called Rio, which is capable of operating from locations on land as well as in air, space, and the oceans. Two receivers were deployed and operated from TOW buoys in the Pacific Ocean. This is the first time that GPS receivers have been operated in open waters for an extended period of time. Data collected between September 1st, 2018 and December 31st, 2019 were presented in this talk. The observed TEC exhibits a clear seasonal dependence characterized by equinoctial maxima in the data at both locations. Both Rio receivers deployed near the geomagnetic radar show 18 to 35% increase in TEC during moderately disturbed geomagnetic periods. Comparison with the IRI 2016 model show good agreement, and it's our vision for the future is to deploy more of these GPS receivers on other buoys to provide an extended coverage of TEC measurements over the ocean surface, where currently we have no capability for making ionospheric measurements. Thank you.